Hello everyone, good evening. I think my voice is audible, right? Everything is clear. Audio and video, everything is clear, right? Can anyone respond? My audio and video is clear, right? Yes, so we'll start. I'll just check this team is correct. A minute. Yes, I think everything is correct. Right? Okay, so we'll start this calculus lecture number 05. So if you haven't watched the previous 4 classes, so I strongly recommend you to watch all the previous classes. So this is calculus 04. So far in differential calculus, what we have did is we have completed, we have started with the limits, right? So limits continued today's class, which is mean value theorem. So we had some quite a long break between calculus 04 and calculus 05. So I strongly recommend you to recall all the previous concepts like the definition of differentiability, and then we have solved many problems based on limits using standard formulas like that, right? So you just recall all that. I already sent all the notes in Telegram. You just go through the notes. Differentiability definition. A function is differentiable at a point if that a left hand derivative and right hand derivative both exist and finite and both are equal. Like that, we update many problems also. So you just recall all that, right? So in this class, we're going to concentrate on mean value theorem. So mainly, I'm going to concentrate on Rolle's theorem and Lagrange's mean value theorem, right? So we will do that. So first, the flow for this lecture will be first I'll be introducing Rolle's theorem. We'll be proving Rolle's theorem, and then based on Rolle's theorem, we'll be doing some 4 to 5 problems, and then we'll be introducing Lagrange's theorem, and then I'll be proving Lagrange's theorem also, right? So I think this will go for 1 hour 15 minutes to 1 hour 25 minutes. So we'll start Rolle's theorem, right? Yes. Okay. So first, what I'll do is I'll just write down the statement of Rolle's theorem. Then I'll explain geometrically. Then we'll move on to proving that Rolle's theorem, right? Okay. If if a function if a function f defined on closed interval a comma b, right? So we have a function that is defined on closed interval a comma b. I think I can change the background, right? White color is, I think, it's very bright. I think so. We'll change to hold background. A minute. We'll choose to our hold background. Yes. So we'll start Rolle's theorem. So first I'll write down, I'll quote Rolle's theorem, then we'll move on to explaining it, right? Okay. So if a function f defined on closed interval a comma b is such that our f of x satisfies the following three conditions, right? The function f defined on closed interval a comma b is such that f of x is continuous. F of x is continuous on closed interval a comma b. So we have a function f of x. In the interval a comma b, it is continuous, right? It is smooth curve. You know the definition of continuity. A function is continuous if it is continuous at each of its point. F of x is continuous on closed interval a comma b, and then f of x differentiable. F of x is differentiable on open interval a comma b. So that function is differentiable. That means doesn't have any sharp edges. And you know definition of differentiability. It is differentiable at each of its point in this interval a comma b. And also we have f of a is equal to f of b. That is output values of a and b are equal. Your f of x satisfies these three conditions. F of x satisfies these three conditions. This closed interval a comma b. Then this will happen. Then there exists a point c in the open interval a comma b. You can always find a real number c in the interval a comma b. Then there exists c in the interval a comma b such that f dash of c is equal to 0, right? We have f dash of c is equal to 0. So we will prove this. You just recall what is the definition of differentiability at a point, right? So you just recall what is meant by f dash of a. What is meant by f dash of a? It is nothing but slope of slope of tangent line, slope of tangent line at x is equal to a, right? At a we have a function value. At function value you draw a tangent line at that point to the curve. The slope of that tangent line is called f dash of a, right? So I'll strongly recommend you to watch the previous videos, because if you watch this video directly then it is hard to visualize for you. I've already explained what is meant by f dash of a, right? The definition of differentiability. So for example, you have some curve, right? At a, this is your function value. This is f of a. At f of a, you draw a tangent line. The slope of this tangent line will be a number. That number will be called as f dash of a, right? This you already know. What this theorem says is we can always find a number c, the interval a comma b, such that derivative of this point is 0. That means what? What is f dash of c? Slope of tangent line, slope of tangent line at x is equal to c. So what we need to do is, if a function satisfies these three conditions, I can always find a number c in the interval a comma b. I can always find one point in the interval a comma b whose derivative at that point is 0. That means at that point the slope of tangent line will be 0, right? Slope of tangent line at x is equal to c will be equal to 0. This is obviously true, right? Why? Because, and also remember, when a slope of when a slope will be 0, when a slope will be 0, slope will be 0 when your line is parallel to x-axis, right? Your line is parallel to x-axis, slope will always be 0, because your y coordinates are same. That means slope will be what? Y2 minus y1 divided by x2 minus x1, right? Okay. So we will have a geometrical proof for this first, then we will prove this mathematically. I'll go a little bit fast, I think. So, okay. Camera. Okay, so we have a function f of x. Let us say this is our value a and this is our value b, right? And you can see that our f of a and f of b are equal. That is, our output values of a and b are equal. Now we are starting at this point. We are starting at this point. We have to reach this, and it means our function is continuous and differentiable, right? That means you can go anywhere, but you have to come down at least one time to reach this point, right? This is our f of a, and this is our f of b. You can go from f of a to f of b in many ways, but if you go in any way, you have to come down at least one time to reach this point f of b, because f of a and f of b outputs are here, right? You cannot say that, sir, I can go like this. Wrong. Here f of b is here, but f of b has to be here. So you can see in this graph, I have come down at least one time to reach this point f of b. Clearly, I can reach this point like this also, right? 1, 2, 3, and then like this. Now, the first graph, that is in the straight line, sorry, white curve, you can see I can always find a point C in between the a comma b, in between a comma b, whose derivative at this point, right? Whose derivative at this point. What is f dash of a? What is f dash of a? Slope of tangent line at c, right? Let us call this as f dash of c. So this derivative at this point will be f dash of c, right? Will be f dash of c, and you can see this line is parallel to x-axis, right? That means the derivative, the slope of this tangent line is equal to 0, because we know that f dash of a is nothing but the slope of tangent line at the point f of a. F dash of c is nothing but the slope of the tangent line at x equal to c. And you can see I can always find a number c. So is 0 because this line is parallel to x-axis. Why? Because if your line is parallel to x-axis, right? That is, this is our x-axis. That is, this coordinate will be what? Some x1 comma y1, and this coordinate will be some x2 comma y2. Now what is slope formula? Y2 minus y1 divided by x2 minus x1. And since the y coordinate are same, let us call this as x1 comma y1 and x2 comma y1, because both the y coordinates are same. If you do slope formula, y2 minus y1 divided by x2 minus x1, you will have 0. That means I can always find a point C. I can always find a point C in between a comma b, whose tangent line is parallel to x-axis. That's what the theorem says, right? And you can see in this curve, I can find many C's. You can see, there is one C here, because for this C, your slope of line will be 0, because you can see this is parallel to x-axis. I can find one more C here, and I can find one more C here. I can find one more C here. Here it is. And I can find one more C here, and I can find one more C here. So for this, you can see C1, C2, C3, C4, C5. So we have 5 C's here. But I can assure you, we can always find at least one C. Then we will rephrase this. There exists at least, this is very important, there exists at least one C in the interval a comma b, such that derivative at this point is 0. What is derivative at that point? It is nothing but slope of tangent line at that point. So we can always find at least one C whose derivative at that point is 0. That means that tangent line will be parallel to x-axis. Right? So we'll prove this. So is this clear? The statement is clear. So I'll just rephrase this. Then there exists at least one C in the interval a comma b, such that f dash of c is equal to 0. What is f dash of c? Slope of tangent line at x equal to c will be equal to 0. Slope 0 means derivative at that point is 0 means slope of that tangent line is 0. Slope of the tangent line is 0 means that line is parallel to x-axis. Right? Okay. So proof. So I'll write down the proof fastly. Let us try to visualize. Right? Okay. Since f is continuous, f is continuous, since f is continuous on closed interval a comma b, therefore it is bounded and attain its bound. Therefore, it is bounded and it will attain its bound, right? And it will attain its bound. Let me draw the diagram. Let's say this is our a, will be my f of a. Let us say this is our f of b, will be b. Let us go, the graph is like this, right? You can see there are many C's here. You can see there is one C, one C, one C, one C, one C, right? 1, 2, 3, 4, 5. There are 5 C's in this graph, for which slope is parallel to, tangent line is parallel to x-axis, right? Okay. So what this line says is, since f is continuous on closed interval a comma b, therefore it is bounded. That means since f is continuous, I can always find maximum value and minimum value. That means it is bounded. Bounded means it is bounded by upper number and bounded by lower number. We can always find maximum and minimum value. And since f is bounded, maximum value and minimum value both will be in your range, right? So that means your greatest lower bound and GLB and LUB both will be in your range. That means it turns out to be maximum minimum value also. I'll explain. Okay. Let capital M is equal to least upper bound of f in closed interval a comma b, and small m be the greatest lower bound of f in the closed interval a comma b, right? See, least upper bound is very simple, right? See, if your f is bounded, then your least upper bound is nothing but your maximum value, and if f is bounded, your greatest lower bound will be your minimum value. So we have, this is our capital M, this is our small m, right? Don't worry about that. Our capital M, this is our small m. So if f is bounded, your upper bound will be your maximum value in your closed interval a comma b, and the lower bound will be your greatest lower bound will be your minimum value in the interval closed interval a comma b, right? So let capital M be the least upper bound of f in a comma b, and small m be the greatest lower bound of f in a comma b. Then there exists point c comma d in the interval a comma b, such that so we can always find a point c and a point d, such that c takes the value small m and d takes the value capital M, right? Such that f of c equal to small m and f of d equal to capital M, right? Now there are two possibilities, right? So we are going to prove this by two cases. So case one, right? So as of now, it's very clear, right? I have drawn the diagram. I have assumed small m to be the least value. I have assumed capital M to be the greatest value, right? And I can always find a point C and D such that C takes the value small m and D takes the value capital M. Now, case one, if what if capital M is same as small m? Can anyone? What is if your capital M is same as small m? That means your maximum value and minimum value both are same. That means your f is nothing but a constant function, right? That means your f is a constant function, yes or no? If capital M and small m are same, then this implies f is a constant function, yes or no? F is a constant function, That means your f of x always takes the value capital M or small m, right? Because both are equal for all x in the interval a comma b. Yes or no? See, if your f of a and f of b, if your capital M is equal to small m, then the graph will be a straight line, right? Horizontal line. Because f of c is maximum, minimum, both are same, right? Okay. So if this happens, then surely that is a constant function. For constant function, we can always find a point C whose derivative is 0 because it is that derivative is 0 throughout for all x, right? That means f of x is equal to m for all x belongs to a comma b. This implies what is your f dash of x? It is 0 for all x in this interval a comma b. Yes or no? For all x in the interval a comma b because it is a constant function. That means I can find infinitely many C. What see if your graph is a straight line for all C in this a comma b, derivative is 0. I can find infinitely many C. That means this theorem is true if your capital M is equal to small m, right? If your capital M is equal to small m, yes or no? That means f dash of C is equal to 0. This implies we can we can find at least one C in the interval a comma b such that f dash of c is equal to 0. So case 1 is true, right? Now case 2, this is our trickiest case. What happens if your capital M is not equal to small m? So in this diagram you can see your capital M is not equal to small m. So we will prove this case. Case 2, if capital M is not equal to small m, right? What is capital M? Is your maximum value and small m is your minimum value. Actually, capital M is your least upper bound. Since your f is bounded, so that means your LUB will be your maximum value and GLB will be your minimum value if your f is bounded. Okay. So if capital M is not equal to small m, um, capital M is equal to not equal to small m, right? Okay. So we will prove this case now. Okay. So we'll prove this now. Um, Actually, I have assumed capital C to be. Let us rewrite this, right? Let us call this as C, call this as B. Let C and D be this, right? So f of C is capital M and f of D is small m. Okay. So if capital M is not equal to small m, right? Suppose for capital M is f of C that we already know, right? Is different from f of A and f of B. Obviously, it is different. F of A, f of B, M all are different. Suppose if capital M is equal to f of C is different from f of A and f of B, right? Now, surely, let us write and then explain, right? So, capital M is your f of C, and we know this is not equal to f of A, and we know this is not equal to f of B, right? If f of C is not equal to f of A, that means C is not equal to A. And if f of c is not equal to b, then that means c is not equal to b. See, I am taking a c in between a comma b only. That means c is not a and c is not b. That means c is not a and c is not b. This implies surely the c will be in the interval a comma b. Right? This will be c in the interval a comma b. Uh, since since f is differentiable at open interval a comma b and c is in the open interval a comma b, that means can I say f is differentiable at x is equal to c. See, in the interval open interval a comma b itself, it is differentiable at each of its point. C is in the interval a comma b. That means it is differentiable at c. Now, since it is differentiable at c, for LH, left hand derivative at C is same as right hand derivative. Yes or no? For LSD is equal to RSD. For LSD is equal to RSD. Right? Okay. Now, What is your left hand derivative at C? What is left hand derivative formula? Limit s tending to 0 f of c minus h minus f of h divided by minus h, right? And what is your right hand derivative formula? R of f dash of c, limit s tending to 0 f of c plus h minus f of c whole divided by h, whole divided by h. Now, and we know these two are equal because it is differentiable. Uh, it is differentiable at c. That means your L of f dash of d is equal to R of f dash of c. Okay. Now, very important point. What is the relation between this f of c? What is the relation between this f of c minus h and f of c? See, c minus h will be somewhere around here. As a result, will be your c minus h, right? This is your f of c minus h. And surely this f of c minus h value will always be less than or equal to capital M. Yes or no? So clearly f of c minus h is always less than or equal to f of c, right? F of c minus h is always less than or equal to f of c. That means your f of c minus h minus f of c is always less than or equal to 0. Yes or no? F of c minus h minus f of c is always less than or equal to 0. And this quantity is negative, right? This quantity is less than 0. Already we have less than 0 quantity here. As a result, overall quantity will be greater than 0, right? This implies where L of f dash of c is always greater than or equal to 0. This quantity is less than 0. This quantity is less than 0. So less than 0 by less than 0 will be greater than 0. Now similarly here, so clearly f of c plus h is always less than or equal to f of c, right? So c plus h will be somewhere around here, and this is f of c plus h, and this value is less than or equal to capital M. That means your f of c plus h minus f of c is again less than 0. That means this quantity, which quantity? So this quantity is less than 0. This quantity is greater than 0. As a result, your overall quantity will be less than 0. So we have R of uh, we have we have R of f dash of c is less than or equal to 0, right? So we have L of f dash of c is greater than or equal to 0, and R of f dash of c is less than or equal to 0. See, we know both are equal, right? Since L of f dash of c is equal to R of f dash of c, this quantity is greater than or equal to 0. This quantity is less than or equal to 0. Both will be equal when? Both will be equal when? This implies your L of f dash of c is equal to R of f dash of c has to be 0. Why these two are equal? Because f is differentiable at x is equal to c. So these two inequality both will be true simultaneously if both are 0. So this implies f dash of c is equal to 0. This implies hence the theorem, hence the proof. There exists a point c whose derivative at that point is equal to 0, right? So very simple proof. If a function f defined on closed interval a comma b is such that if your function is continuous in that interval, differentiable in that interval, f of a and f of b are equal, then I can always find a number c in the interval a comma b whose derivative at that point is equal to 0. So I have assumed capital M small m to be the maximum minimum value. I have given c and d to be the f of c is capital M and f of d is small m. Case 1, if capital M, small m both are equal, then it is a constant function. So obviously your derivative is 0. We can always find a point C whose derivative is 0. If capital M is not equal to small m, very simple, right? At that, suppose m is equal to f of c is differentiable. See, I have shown for capital M. Similarly, you can also show for small m also. See, why I'm showing for capital M, because see 12th standard mathematics, right? So maxima, minima. So maxima, minima always occurs at critical points, right? So for critical points, your derivative is always equal to 0. That is why we are choosing maxima, minima value. Okay. Similarly, you can show your similarly, you can show f dash of d is also 0. This is your d. This is your f dash of c, right? F dash of c is 0 because c is this value. Similarly, you can same way you can show f dash of d is also 0 because your small m is f of d and this d is differentiable. That means your L of f dash of d is equal to R of f dash of d. And similarly, you can put the same result using small m also, right? Similarly, when small m is equal to f of d, we can do the same as f dash of d is equal to 0, right? So that's it. If your function is continuous on this interval, differentiable in the interval, you can always find a number c whose derivative is 0. See, uh, as of now, there is no, this kind of theorem is not asked. Uh, as of now, this kind of theorem is not asked in exam, but it's always nice to read the theorems with the proof, right? Suppose if they ask, you should have some idea to prove, right? That's why I will not skip the proof of some important theorem. Okay. See, what this theorem says is if your function satisfies, see, this is a if then only. If then means if this satisfies, then this will happen. If this happens, this need not be true. If implies then will not imply if, right? So I'll give a counter example that failure of Rolle's theorem. Failure of Rolle's theorem. See, what Rolle's theorem says is if your function satisfies these three conditions, then this will happen. What is if three conditions? What is three condition? Continuous, differentiable, and f of a and f of b are equal. Then we can always find a number c whose derivative is equal to 0. If if this if this happens, then this need not be true. That is, if there exists a point c whose derivative is 0, then your f need not satisfy that three condition. That is f of a and f of b are equal, continuous, differentiable, right? I'll give a counter example. I'll give a counter example. I'll give a counter example. You consider the function. You consider the function 0 uh, when x lies between 0 to 1, and it is x plus 1 when your x lies between 1 to 2, right? I'm defining some break function. So how I'm defining a function is, so from 0 to 1, it is a constant function which is 0. From 0 to 1, it is a constant function which is 0. At 1, this function is not defined. It will be tending to 2, right? At 2, it is 3, and then it is a straight line. The function is like this, right? Here we have an horizontal line, and then some line with the slope, and this point is not defined. Now you can see that I can find a point C in the interval 0, 1 whose derivative at that point is 0. I can find infinitely many C here, right? For example, here let us take C is equal to 1 by 2. This 1 by 2 belongs to the closed interval 0, 2, right? I'm defining a function f from closed interval 0, 2 to R. Let us define from R. You can see this number C, the interval 1, 2. You can see for f dash of c is 0 at that point, right? Because derivative at any point is 0. But you can see your f of x is not differentiable because you can see it has sharp edge here. It is not continuous also. It is, and f of 0 is also not equal to f of 2. You can see all three condition fails, but even though I can find a point C in the interval a comma b whose derivative is 0. If these three happens, then we can find a point C whose derivative is 0. If you can find a point C whose derivative is 0, then it need not be that your f is continuous, differentiable, and f of a and f of b are equal. Converse, converse is not true, right? Converse is not true. Converse is not true, right? Okay. Uh, so I think we can move on to problems now. So as of now, we have defined Rolle's theorem, and then we have discussed about the failure of Rolle's theorem. That is, the converse of the Rolle's theorem need not be true, right? And Rolle's theorem is valid only if the three conditions are satisfied. Okay. So we'll do some problems now. We'll start with basic problems. Verify Rolle's theorem. Arun, yes. Verify Rolle's theorem for f of x is equal to e power x sin x, the interval 0 comma pi. So verify Rolle's theorem for the function f of x equal to e power x sin x in the interval 0 comma pi. Verify Rolle's theorem means you have to prove that there exists a number c in the interval 0 comma pi whose derivative at that point is equal to 0. So we'll prove this. So we have f of x is equal to e power x sin x, and you can see this function is continuous, it is differentiable also. You can see what is the value of f of 0. The f of 0 is e power 0 sin 0, e power 0 is 1, sin 0 is 0, and what is f of pi? The f of pi is e power pi sin pi, again sin pi is 0, and you can see your f of 0 is same as f of pi, and also f is continuous and differentiable on the interval 0 comma pi, right? Continuous means closed interval, differentiable means open interval, right? Why? Because you can see it is continuous and differentiable because individually sin x is continuous, e power x is continuous. That means product of continuous function is continuous function and product of differentiable function is differentiable function, right? So we have e power x sin x, e power x into sin x. This is continuous, this is continuous. As a result, product will be continuous, right? And similarly, both are differentiable function, both are smooth functions. So that means our f satisfies all three conditions for Rolle's theorem. That means we need to show that there exists a number c in this interval whose derivative is 0. Let us try to find f dash of x. So what is f dash of x? Just differentiate this e power x product rule. If I differentiate sin x, it is cos x plus differentiate e power x. So let us take e power x outside. We will have sin x plus cos x. So f dash of x equal to 0. That means e power x sin x plus cos x equal to 0. E power x will never be 0, right? Because e power x is always positive. Range of e power x is open 0 to infinity. So this is always greater than 0. That means this implies sin x plus cos x is equal to 0. This means sin x is equal to minus cos x. This means sin x by cos x is equal to 1, equal to minus 1, and this means tan x is equal to minus 1. So when tan x will take minus 1 in the interval 0 comma pi, I think it is 3 pi by 4, right? So tan 3 pi by 4 is pi minus pi by 4. So pi minus pi by 4 will be in second quadrant. In second quadrant, the tan is negative, so it is minus tan pi by 4. So x is equal to 3 pi by 4. And you can see this 3 pi by 4 is in the interval 0 comma pi, right? So, uh, so we have a real number c, which is 3 pi by 4, and that belongs to the closed interval 0 comma pi, such that f dash of c is equal to 0, because we have got 3 pi by 4. How? Because we are finding a point whose derivative is 0. It turns out to be when c is equal to 3 pi by 4, the derivative is 0. That means this 3 pi by 4 is in this interval also. So we can always find a number c. We can find we need to show there exists at least one c. We say that there exists one c in this interval for which f dash of c is equal to 0. Right? So we have verified Rolle's theorem. We move on to next theorem, next problem. So problem number 2. If see, I'm just omitting all basic problems, right? They will that kind of basic problems that are not asked by exam. So I'm just neglecting very basic problems like verify Rolle's theorem for some function. You know how to do, right? 12th standard level problem. You say that f of a and f of b are equal. You say that it is continuous and differentiable. You find the slope. You find f dash of c is equal to 0. You see how many c's are there in the interval a comma b. That you can do, right? In Telegram group, I'll send some practice problems based on like the problems. If f of x, g of x, and h of x, f of x, g of x, and h of x have derivatives when your x lies between a to b, so that there is a value of c, so that there is a value of c, uh, so there is a value of c of x in the interval a comma b, such that determinant of f of a, g of a, h of a, f of b, g of b, h of c, f dash of c, g dash of c, h dash of c equal to 0. H dash of c, h dash of c is equal to 0. So what I need to do is we have three functions. We have three functions f, g, and h, and all these functions are differentiable for all x the closed interval a comma b. Then we need to show there is a value of c of x. That is not a problem. We need to show there exists a number c in the interval a comma b, such that such that this happens, right? So we will do this. Let us consider. Let us see. Defining a function is an art, right? Defining a function is an art. Uh, let us define a function as f of x is equal to f of a, g of a, h of a, f of p, g of b, h of c. Instead of f dash, g dash, c dash, let us define as f of x, g of x, and h of x, right? Let us define a function like this. Now, this capital F of x satisfies all three conditions of Rolle's theorem. Why? Let us try to expand this. See, if you try to expand this, what you will have? See, if you try to expand this, what you will have is some some number into f of x, some number into g of x, and some number into h of x, right? Don't worry about the coefficients or constant term. If you expand this, you will have f of a into g of b h of x minus h of c g of x, and you will be having some set of one set of long equation. Everything will be some constant multiplied by f, g, and h. Let us call that as some a into f of x, b into g of x plus c into h of x, where this a, b, c are some real constants, right? Now, I'm going to say that this capital F of x satisfies all three definitions of Rolle's theorem. F of a is equal to f of b, both are 0. Why? Why? What happens if you put x is equal to a? What will be your f of a? F of a will be what? F of a, g of a, h of a. And you can see that R1 and R3 are identical. If the rows are identical, determinant will be equal to 0. That means your f of a is 0, right? And what about f of b? Already, see, these two are fixed. There is no x here. F of b will be small f of b, small g of b, small h of b. And again, you can see R2, R3 are identical. Again, the determinant will be 0, right? Uh, you, if you put in capital F of x, rows will be identical. As a result, your determinant will be 0. Also, your capital F of x is continuous and differentiable in where? In the interval closed interval a comma b, right? Continuous in the interval closed interval a comma b, differentiable in the interval, differentiable in open interval a comma b. Why? Why? Because your capital F of x is a linear combination of functions of small f, small g, small h. Already small f, small g, small h are continuous and differentiable. So sum of functions is also continuous and differentiable, right? By sum of continuous and differentiable function is continuous and differentiable. Individually, all are continuous and differentiable. That means our capital F of x satisfies satisfies the conditions for Rolle's theorem. Satisfies the conditions for Rolle's theorem. That means there exists a number c, or there exists a number x, there exists a number, okay, let us write this as f dash of c itself. There exists a number, there exists at least, there exists at least one c in the open interval a comma b such that f dash of c is equal to 0. Now, what is our capital F dash of c? Because our capital F satisfies, right? Now, what is our f of x? Capital F of x is a into f of x plus b into g of x plus c into h of x. Now, what is f dash of x? A into f dash of x, b into g dash of x, c into h dash of x. And we know there exists a number c such that f dash of c is equal to 0. That means a into f dash of c plus b into g dash of c plus c into h dash of c is equal to 0. Right? So this c and this c are different. This c is just constants, right? Okay. Or else can we write PQR so that you won't confuse that this capital ABC with this small c. Let us write this as some PQR on some constants PQ and R. Right? Let us write PQR. so that you won't confuse with this capital ABC and this ABC. P comma Q comma R. Okay. See, can I write this as like this f of a, g of a, h of a. I'll get back the substitution f of a, g of a, h of a, f of b, g of b, h of c, f dash of c, d dash of c, s dash of c is equal to 0. Can I write this as like this? When you expand this, you will have some constant multiply with this, coefficients multiply with this. So, hence the proof. So you just have to remember that you have to define a function capital F of x as f of x, g of x, h of x, and you have to show this capital F of x satisfies the conditions of Rolle's theorem. That means you can find a number c in the interval a comma b such that derivative is 0. Then the problem is very simple. We'll move on to problem number 3. We'll move on to problem number 3, right? Show that show that between any between any two roots of e power cos x equal to 1, there exists there exists at least one root there exists at least one root of e power x sin x minus 1 equal to 0. Okay. So the next theorem is show that between any two roots of e power x cos x equal to 1, there exists at least one root of e power x sin x minus 1. Right? So very simple, right? So I'll just visualize this. Okay. So we have e power x cos x minus 1, right? So you can see this is the graph for e power x cos x minus 1. Let us try to draw one more graph, which is e power x sin x minus 1, right? You can see blue graph is our blue graph is our what? Blue graph is our red graph is e power x cos x minus 1. So you can see there are between two roots of e power x cos x minus 1, there is one root of e power x sin x minus 1. Right? You know what is root, right? It's a point where crossing the x-axis. If you see, you take any two roots, right? You take any two roots of e power x cos x minus 1, there will be a root of e power x sin x minus 1, right? It is true for any you can see this one and this one are two roots, and you can see in between there is one root of e power x sin x minus 1. Similarly, you can see between these two roots, you can see one root of e power x sin x minus 1, right? If you take any two roots, for example, if you take this root and this root, you can see 1, 2, 3 roots are there. So between two roots of e power x cos x minus 1, at least there will be one root of e power x sin x minus 1 is equal to 0. right? This is what the next problem is. So we'll prove this now. Yes. So show that between any two roots of e power x cos x is equal to 1, there exists at least one root of. It need not be a conjective roots, right? Um, it need not be the next to roots, right? Okay. Uh, so we'll move on to proving this. Show that between any two roots of e power x cos x equal to 1, there exists at least one root of e power x sin x minus 1 is equal to 0. Okay. So let x is equal to a and x is equal to b be two distinct roots. Be two distinct roots of e power x cos x equal to 1. Since a and b are roots, that means a will answer this equation. That means e power a cos a is equal to 1. That means can I write cos a as e power minus a? And similarly, b is also root. So e power b cos b is equal to 1. Can I write cos b as e power minus b? Right? As e power minus b is 1 by e power b and both are true. Call this as equation number 1. Let us consider the function. Consider the function. I'm going to define a new function. Let us define the function as capital F of x. Let us define the function as e power minus x minus cos x. You have to remember this function, right? You have to remember this function. I'm just defining the function as e power minus x minus cos x. Now I'm going to show that this function satisfies all three conditions of Rolle's theorem. Clearly, what is f of a e power minus a cos a, and this is 0 because e power minus a is same as cos a, so cos a minus cos a is 0, and this f of b is e power minus b minus cos b, and this is also 0, right? Uh, so we have f of a is equal to f of b is equal to 0, right? F of a is equal to f of b is equal to 0, and your capital F of x is continuous and differentiable. Why? Because this is continuous, this is continuous. So difference of two function is continuous, and again difference of differentiable function is differentiable also, right? This is continuous, continuous individually. This is continuous, continuous. So difference is also continuous, and similarly it is differentiable. That means our capital F of x. So okay, for that we have f of x. So we have capital F of x satisfies satisfies all conditions of Rolle's theorem, right? This implies this implies there exists a number x in the interval a comma b such that f dash of x is equal to 0. Now what is f dash of x? What is our f of x? We have defined f of x as e power minus x minus cos x. So what is f dash of x? Minus e power minus x. Derivative of cos x is minus sin x is equal to 0. So that means this is e power minus x plus sin x is equal to 0. So sin x is equal to e power minus x. Sin x is equal to 1 by e power x. This implies e power sin x is equal to 1. This implies e power sin x minus 1 is equal to 0. That means we have showed an x in the interval a comma b such that e power x sin x minus 1 is equal to 0. That means this implies what? there is a root x in the interval a comma b, because e power x sin x minus 1, there is a root of e power x sin x minus 1 in the interval a comma b. A and b are roots of e power x cos x minus 1, the interval a comma b. Hence the proof. E power x minus e power x sin x minus 1 is it clear? Show that between any two consecutive, sorry, not consecutive, show that between any two roots of e power x cos x equal to 1, there exists at least one root of e power x sin x minus 1 equal to 2. Similarly, we will do one more problem based on the same idea. Problem 4. You are going to do this. Show that, prove that between, any two real roots, of e power x sin x is equal to 1, there is at least one real root of e power x cos x plus 1 is equal to 0. I think I do this right. The same, it is slightly altered, right? Here we have e power x sin x equal to 1. Here we have e power x cos x equal to 1. Here we have e power sin x equal to 1. And here we have e power x cos x plus 1 is equal to 0. Right? Here both are minus 1, minus 1. Here 1 is plus 1 and again is minus 1. So here you can see that e power x sin x minus 1, and another is e power x cos x plus 1. And you can see between any two roots of blue, there is one root of green, right? There is one root of green graph, right? You can see that between any two roots of blue, there is one root of green. And if you take this root and you take these two roots, what in no, actually e power x sin x minus 1. So okay, between any two roots of blue, there is one root of green, right? You can see between any two roots, of blue. So let us say this is our first root, this is a second root. You can see 1, 2, 3 roots, but I can always find at least one root between any two roots of e power x sin x minus 1, right? This is what the next is. I think you can do the same thing, right? You define a function, the same idea. What I'm going to do is same idea, right? You define your function capital F of x as, uh, do they need to prove or you can prove? Same thing, let x is equal to a and x is equal to b, two distinct roots of e power x sin x is equal to 1. That means e power a sin a is 1, e power b sin b is 1. That means sin x is e power minus a, sin b is e power minus b. Call this equation number 1. To define capital F of x as e power minus x minus sin x. So instead of cos x, you define as minus sin x, right? Okay. You define capital F of x as e power minus x minus sin x and proceed as before, right? You can do this easily. Just the same thing, wherever you see cos x here, you just replace as sin x. You will end up with the proof of. We'll move on to problem number 4. Take this exercise. Move on to problem number 5. Or else should I need to prove? So I'll do this very fast. Let x is equal to a and x is equal to b be two distinct real roots of e power sin x equal to 1. So that means e power a sin a is equal to 1 and e power b sin b is equal to 1. So we have e power minus a is sin a and we have e power minus b is sin b. Right? Call this as equation number 1. Now you define capital F of x as e power minus x minus sin x. Right? Now your capital F of x satisfies satisfies the conditions of Rolle's theorem. Why? Because your f of a and f of b both are 0 and your f of x is continuous and differentiable. So for explanation, refer the previous problem. So that means this implies there exists at least one x, the interval a comma b, such that f dash of x is equal to 0. Let us write as capital F dash of x. Now f dash of x is equal to 0. So what is the differentiation of e power minus x minus sin x? So it is minus e power minus x and derivative of sin x is cos x is equal to 0. So we have cos x is equal to e power minus x. We have cos x is equal to 1 by e power x. So we have e power cos x is equal to 1. So we have shown there is one root of e power x cos x minus. Okay. So this implies e power x cos x plus 1 is equal to 0. This implies x is a root of e power x cos x plus 1 is equal to 0 because or else you can also write as some c, right? F dash of c is equal to 0. That means c is a root of e power x cos x plus 1. So hence problem the proof. Okay, we'll move on to problem number 5. Just a minute. Move on to last problem of Rolle's theorem. By considering the function by considering the function x minus 4 log x, show that the equation x log x equal to 4 minus x is satisfied by at least one value of x lying between 1 and 4. Okay, so we have a function f of x is equal to x minus 4 log x. By considering the function f of x is x minus 4 log x, so that the equation is satisfied by at least one value of x in the interval 1 comma 4. So in the interval 1 comma 4, you can see this f of x satisfies the definition of Rolle's theorem. Conditions of Rolle's theorem. What is f of 1? This is x minus 4 log 1. This is 0. And what is f of 4? Again, this is 0. And clearly, your f of x is differentiable and continuous in the interval 1 comma 4. That means there exists at least one c the interval 1 comma 4, or let us say 1x, such that f dash of x is equal to 0. Now what is derivative of x minus 4 log x? Let us keep x minus 4 as it is. Derivative of log x is 1 by x plus, let us keep log x as it is. Derivative of x minus 4 is 1, right? So if I multiply this, we will have x minus 4 plus x log x is equal to 0. If I take that side, we will have x log x is equal to 4 minus x. So we have proved that there is a show that the equation x log x is equal to 4 minus satisfied by at least one value of x. Be true by Rolle's theorem, right? So we are done with the Rolle's theorem. The next class we will start Lagrange's theorem, and then we'll introduce Cauchy's mean value theorem, right? So that's it. So we'll wind off this class. So in this class we have started with the Rolle's theorem, and then we have solved some 5 problems based on Rolle's theorem, right? Thank you. All the best. We'll see you in the next class. Thank you.